So in this video lecture we will be calculating the electric field due to hemisphere. So let's say we have a hemisphere of radius r, something like this. This is a hemisphere of radius r. We have to calculate electric field at this point P. This hemisphere is having charge like sigma coulomb per meter square. So this is surface charge density. R is the radius of the hemisphere. Now if we have to calculate the electric field at this point P, for that what is required is we have to take a ring at some angle theta by considering an elemental angle of d theta like this. Here we can consider this elemental ring. This is a ring like this. Okay. So what we are required here is to find the charge on the ring. Let's say that charge to be dq. Then dq will be, this is obviously rd theta. Then the charge on this ring will be the area of this ring into sigma. The radius of this ring, if we try to find, then we can see that this is r, this is theta, so this will be r cos theta. Similarly this will also be r cos theta. So the radius of this ring is r cos theta, so the circumference will be 2 pi r cos theta into this height of the ring, which is r d theta. So this is the area of the ring into sigma, this is the charge. Now we can easily see that this point P is at axis of this ring, and at axis of ring, electric field, as we have seen in previous lectures, can easily be used kqx by x square plus r square to the power 3 by 2. So this is the electric field at the axis of. So if we use this result with this dq, then we can easily find the electric field at this point P. So small electric field due to this small elemental ring will be k dq, which is 2 pi r cos theta into r d theta into sigma upon x square plus r square to the power 3 by 2. This is the radius of ring. This is the radius of ring. This is distance of point P from center of ring. This is the distance of this point P from the center of the ring, which is r sin theta. So k q x, in place of x I have to put r sin theta, kqx upon x square plus radius of ring, which is r cos theta square to the power 3 by 2, and then integrated. So this way I will get electric field at point P. Here I can see that this is r square sin square theta plus r square cos square theta, that will become r square to the power 3 by 2, that is r cube, and in numerator I am also seeing r, r and r. So this r cube and in denominator will get cancelled by the r cube in numerator. So what I'll get is k 2 pi sigma as constant, sin theta cos theta d theta integration. Let's put this 2 also here, and the limit of this integration will be only 0 to pi by 2, because when I'm taking limit 0, then I'm almost getting this ring, electric field due to this ring, and when I'll get angle 90 degree, I'll get the electric field of this ring. So you can see that just by varying my limit from 0 to 90 degree, I'm covering the whole hemisphere. So the limit from 0 to 90 is more than sufficient. People might consider the limit to be 0 to 180, but you should be aware of it that limit will only be 0 to 90 degree, right? So I keep here k pi sigma. 2 is with this sin theta and cos theta, so this is sin 2 theta d theta integration. Now this is k pi sigma. The integration of sin 2 theta is simply minus cos 2 theta by 2 with limit 0 to 90 degree. So k pi sigma with minus cos 2 theta, cos 2 into 90, which is cos pi, which is minus 1, minus cos 0, which is 1. So and by 2 is also available here. So what I get here is minus k pi sigma minus 2 by 2. So this minus gets cancelled with this minus, and 2 by 2. So what I get is pi k sigma, or if I put the value of k, which is 1 by 4 pi epsilon naught, then what I'll get is sigma by 4 epsilon naught. So this is the answer. Okay.